Welcome to this explainer. Look, if you're a focused learner trying to really get a grip on linear algebra, you are definitely in the right place. Today, we're going to completely rethink how we view matrices. Most people look at a matrix and just see a rigid, kind of boring grid of numbers. But we're going to reframe that entirely. We're going to look at matrices not as static tables, but as dynamic machines that transform data, rotate space, and reveal some seriously incredible hidden structures. To set the stage, let's start with this profound thought from the mathematician Cantor. He said, "The essence of mathematics lies in its freedom." Now, at first glance, a matrix looks like the exact opposite of freedom, right? It looks like a super strict spreadsheet. But as you'll see by the end of this explainer, these strict rules actually give us the absolute freedom to manipulate vast amounts of information and uncover beautiful hidden symmetries.
Here is our roadmap for today. First, the multiplication engine. Second, order matters. Third, the flip. Fourth, perfect mirrors. Fifth, opposites. And finally, number 6, the ultimate breakdown. Okay, section 1, the multiplication engine. Let's dive right into our first core mechanic.
When we multiply matrices, we really aren't just doing basic arithmetic anymore. We're running a highly specific procedure. And before we can even turn the key in the ignition, we have to satisfy the golden rule. If you want to multiply matrix A by matrix B, the number of columns in matrix A absolutely must equal the number of rows in matrix B. If they don't match up perfectly, the engine won't start. The whole operation is just entirely undefined.
But once that rule is met, how does the engine actually run? Well, we use this really tactile row-by-column process. To find a single element in our new product matrix, let's say the element in the ith row and kth column, you literally grab that entire ith row from the first matrix and the entire kth column from the second matrix. You match them up element by element, multiply those pairs together, and then just add up all the resulting products. It's a very dynamic sweeping motion. You go across the row of the first and down the column of the second.
Section 2. Order matters. Non-commutativity. Now that we have the engine running, we need to introduce a major plot twist.
So what's really interesting here is that matrix multiplication breaks a fundamental rule of regular numbers. With normal algebra, 3 times 4 is exactly the same as 4 times 3. But with matrices, order is literally everything. Matrix A times matrix B is generally not equal to matrix B times matrix A. In fact, sometimes AB is perfectly valid to calculate, but BA is mathematically impossible. And even when both are possible, the resulting matrices are usually completely different. It's totally a one-way street.
Section 3, the flip. Matrix transposes.
All right, let's shift gears from arithmetic to a purely spatial transformation.
We call this tool the transpose. We denote it by an A with a little prime mark or a tiny t. Taking the transpose of a matrix simply means we are grabbing the matrix by its main diagonal and flipping it. Every single row becomes a column, and every column becomes a row. It's a literal rotation of the entire data structure.
And you can clearly see the mechanics of that flip in action. Just picture a tall 3-row by 2-column matrix instantly transforming into a wide 2-row by 3-column matrix. An element sitting way down in the 3rd row 1st column perfectly swaps over to sit in the 1st row 3rd column. It is just such an elegant, seamless spatial swap.
Let's quickly see how this builds our toolkit with 4 key rules. First, if you flip a matrix that's already flipped, it just goes back to normal. Makes sense, right? Second, if you multiply by a scalar constant, the flip doesn't care at all. The constant just hangs out. Third, flipping 2 added matrices is exactly the same as adding their individual flips. But pay close attention to that last one. It's the reverse order rule. The transpose of a multiplied matrix AB is actually equal to B transpose times A transpose. Notice how the order magically reverses itself?
Section 4. Perfect mirrors. Symmetric matrices. This spatial flipping leads us right into a really satisfying concept.
I want you to imagine what happens if you take a matrix, execute that perfect diagonal flip we just talked about, and absolutely nothing changes. We call this a symmetric matrix. It's a square matrix where A transpose perfectly equals A. If you draw a line straight down the main diagonal, the top right triangle of numbers acts as a flawless mirror image to the bottom left triangle. Element Aij exactly equals element Aji. It's just absolute mathematical symmetry.
Section 5, opposites. Skew-symmetric matrices. So a symmetric matrix reflects perfectly, but what if the flip gives us something else entirely?
Enter the skew-symmetric matrix. This happens when the flip yields the exact negative, so A transpose equals negative A. If you swap the rows and columns, every single number becomes its opposite sign. But think about the hidden consequence of this rule. What about the elements resting right on that main diagonal line? When you flip the matrix, a diagonal element doesn't move. So, if the rule holds true, it has to equal its own negative. Well, what's the only number in the universe that equals its own negative? 0. Therefore, every single diagonal element of a skew-symmetric matrix absolutely must be 0.
Section 6, the ultimate matrix breakdown. We have finally arrived at the climax of our explainer.
We're going to synthesize all these tools, multiplication, transposes, perfect mirrors, and exact opposites, to prove a massive underlying truth. The crucial point is established with Theorem 1. Take absolutely any square matrix. Seriously, it does not matter how messy the numbers are. If you add that matrix to its own transpose, you will magically create a perfectly symmetric matrix every single time. And if you subtract its transpose from itself, you will always generate a skew-symmetric matrix. It is literally like we found a machine that forces symmetry right out of pure chaos.
Which brings us to the beautiful resolution in Theorem 2. Because of what we just proved, any square matrix in existence can be broken down and expressed as the sum of a symmetric matrix and a skew-symmetric matrix. As the formula shows, you just take half of the symmetric part we generated and add it to half of the skew-symmetric part. Every single square matrix is secretly just a perfect mirror and its exact opposites stacked on top of each other.
Take a second and just think about that. Even the most complex, random-looking data structures have these elegant, balanced foundations hiding right beneath the surface, just waiting for us to uncover them. If every matrix hides a perfect mirror and its exact opposite, what other hidden structures are out there waiting to be flipped, rotated, and discovered? This is exactly the freedom Cantor was talking about at the very beginning. By mastering these strict rules of linear algebra, you now have the freedom to see the hidden blueprints of data itself. So keep exploring, and I'll catch you in the next explainer.